Let's start today picking up where we left off last time, which was the idea that finding the derivative of a function of two variables might be a little bit trickier than we would have first thought. To motivate why this might be the case, let me start off with this little example. Let's suppose that we had a function of two variables, and so here's its graph, which is the equation z equals f of xy. I'll take some input point in the plane, so here will be the point x naught, y naught. And so this input point will correspond to some dot here on the graph, and that dot will be the pair of the order triple x naught, y naught, f of x naught, y naught. So I could ask you this question. What's the slope at this point? How would you find it? Well, before you try to come up with some clever technique for finding the slope of it, I want to point out that that question is actually pretty badly phrased. And to give you some idea about why it's badly phrased, let's look over here at a variation of it. Imagine that your surface had just been a flat plane, and the point that we're doing all of our measurements from are the origin. And so if I asked you, what's the slope at this point right here? In other words, the rise over the run. Well, if you're on the surface and you walk in any direction in the xy plane, your rise is always zero because the plane is flat. And so that would mean that this would sort of unambiguously be slope zero. You don't rise or fall on this surface at all. But let me add a monkey wrench to this. Instead of it being a flat plane, imagine we take a plane that passes through the y-axis, but is angled at 45 degrees. Now what's the slope at zero? If I were to walk in the y direction, then I would stay on this plane. I wouldn't get my z value wouldn't change. I would have no rise in the y direction. And so the slope would be zero. However, if I were to take this point and start moving in the x direction, then I would start to fall on this surface, right? This is the x direction pointing here. Every time the input value moves this way, its corresponding output value would drop. In fact, because this is a 45-degree angle right here, it drops every unit. It drops negative x units for every x units across it goes, which would mean that in the x direction, it has a slope of -1. The z value drops 1 unit for every unit you walk in the x direction. So what's the slope supposed to be? Does it make sense to ask this? How will we fix this problem? We'll fix it by modifying the question. We won't ask for the slope at a point. We'll simply ask for the slope in a certain direction. And at least that question we have some hope of being able to answer. So let's start by asking the question, what's the slope of this point in the x direction? Well, how would we figure that out? Well, imagine I draw this line right here. And so this line just represents lots and lots of little points, input values, where I've moved the value x naught, y naught a little bit in the x direction. Each one of these values would correspond to a different y value on the surface. In fact, if I were to take my initial point and move him all over the x-axis, then all of those z values will go up to the top, and I'll see a shape who looks something like this. What actually is that shape? Well, if you stare at this long enough, you could imagine drawing a plane cutting up through the x-axis. And this plane will intersect the surface. And so when the plane intersects the surface, we're going to see a curve. And remember from a couple days ago that we call these curves traces. Now what trace is this? Everybody on this plane has a y value of y naught. So this is the plane y equals y naught. And we've intersected it with the graph of our function f of z, or z equals f of x, y. And so if I were to look at only the zx plane, or the zx direction, say I stare straight down the y-axis, then I would see this curve right here. I would see the point x naught down at the bottom, and I would see its y value up here. What is this curve? Well, it's on the surface, so it has to look like z equals f of xy, but it's also on the plane y equals y naught, which means that this y value had better be the constant y naught. And so that's the graph we're looking at. Now, if I wanted to figure out the slope in the x direction, well, that's just the slope of this one slice. So if we work out the slope right here, then that would be the slope on this surface right here in the x direction. So how would you find the slope? Well, since this is now a one-variable problem, that's easy. What we're going to do is we're going to take the derivative of f of x, y naught. Now, I made a to-do at the end of the lecture last time that says, well, how do you differentiate a function with two variables? This isn't a function of two variables. This is constant. So what we really have here is we have a one-variable derivative, and it's going to measure the slope in the x direction at the point x naught, y naught. And then once I have this value, I will plug in x equals x naught, and that will give me the slope in the x direction. Well, what if you wanted the slope in the y direction instead? So in other words, you want to take this point right here, but you only want to move the input value up or down in the direction of y. Well, why don't we use the same trick? We'll take a plane who cuts through this point that's parallel to the y-axis, and we'll intersect it with the surface. We'll get something that looks like this. As before, the intersection of the plane and the surface will give me a trace, and it's a trace who runs parallel to that y-axis, so it's only tracking motion in the y direction. Well, how would we find the slope of this trace? We'll do the same thing we did before. We can look down the x-axis. When we look down the x-axis, we'll see the y-axis going this way and the z-axis pointing up. And we're going to see this curve sort of shaped something like this. And here will be the point y naught. Now, what is this curve right here? Well, it's part of the surface, so we know it has to look like z equals f of x, y. But that's a function of two variables. However, the orange trace also belongs to the plane x equals x naught, and so we get traces by replacing the variable x by the number x naught. And so this is the curve that we're looking at, z equals f of x naught, y. It's a function of only the variable y. So now that I've got this point, I could go up to the top, find out where the dot is on the graph, and I could work out the slope of this one right here. So to find this slope, we need to take a derivative. Now remember that y is the variable, so it's going to be the derivative with respect to y of what function? Well, it's the function f of xy, except that x is now a constant. It's the point x naught. So this is really a function of one variable. Once we take the derivative, we'll plug in y equals y naught. And so that's going to get us the slope in the y direction at x naught, y naught. And so now at any point on any surface, we can find the slopes in the two directions. Let's give this a shot on an example. If f of xy is the function x squared plus y squared, find the slopes in the x and y directions at the point 1, 2. I'm going to attempt to graph this thing. And actually, we did it already. We graphed x squared plus y squared before, and that was the graph who was shaped like the cup, the parabola. And so we've got this point who's 1 unit over, 2 units up. So sort of this point right here on the parabola. Let's at least see if we can get an intuitive sense of what we think these things are right here. If I wanted to go and find the slope in the x direction, then I'm at this point right here. I'd only want to change the x values, but not the y values. So I would cut it through with a plane like this. When I cut it through the parabola, I'd see a shape that looks something vaguely like that, because this part of the lip will stick out. And so the slope is going this way. Notice that as I move to the right, it's pointing upwards, which would give me the idea that I would expect this slope to be sort of positive. I really can't figure out the magnitude of it based on my picture because it's not fairly well drawn. So let's instead go and do the algebraic version of this. So how do we do this algebraically? Well, first off, we took the function f of x, and we fixed all of the y values at 2. So the function f of x2 would be x squared plus 2 squared, or x squared plus 4. Now that I have a function of one variable, I can take the derivative of it. In this case, I'll get 2x, and then I'll plug in the value x equals 1. and so we get a grand total of 2. So that's the slope in the x direction. For the y slope, I take my input value and I think of changing only its y values but not its x. So I'd go through and I would slice this with a plane right here. I'd have a slice with something vaguely like that, and so I'd be looking for a slope like this. And once again, it appears as though the slope is rising as I'm moving to the right, so I would expect to see a positive slope in the y direction. But let's compute it exactly. So what's the slope in the y direction? Well, to first figure it out, we have to take our function of 2 variables and turn it into a function of 1 variable. Since I want to change y, I'll leave the x value fixed at 1. And so this is going to get me the equation 1 squared plus y squared, or y squared plus 1. Now that I have a function of 1 variable, I can take the derivative of this function of 1 variable. The derivative of y squared plus 1 is 2y. And if I plug in my input point of y equals 2, then I'm going to get 2 times 2, which is 4. Now my graph doesn't seem to suggest this at all right here. I only got the positive bit right. But what it looks like is it looks like the slope in the x direction at the point 1, 2 is equal to 2, and the slope in the y direction at the point 1, 2 is equal to 4. If we had a better graph, we might be able to check this out visually. So maybe we can have Maple go and do this for us really quick. So here would be the surface we were just talking about, that parabola. Now, as I move it around, I can see it's a pretty tall looking shape right here. We're sort of focused on what happens at the point 1, 3. And so the point 1, 3 is right here. Now if we look at the point 1, 3, which is this dot on the graph, we want to figure out what the rates of change are on this graph in the x and the y directions. Now to figure out the rate of change in the x direction, moving left and right, x direction, I'd want to set y equal to 3. Now if I do that, we could slice this surface with the plane y equals 3. And so we see how it cuts right through this plane right here. Now, if we take a look at where that cut occurs right here, well, we were looking at the tangent line right around this point. And it certainly seems like a tangent of 2 going up 2 units for every 1 unit across is pretty appropriate right there. Now you might say, well, doesn't that look more like a negative 2? But remember, the x-axis is moving, positive direction is moving towards the right. So if I were to sort of turn the graph around and look at it, say, from the inside right there, I would be seeing a positive slope as I move to the x, but its magnitude certainly seems to be consistent with 2. Now, on the other hand, if we were to slice it through with a plane in the other direction so that we keep the y value fixed but change the x value, so we'd want to set x equals 1. So let's do that. First we'll get rid of this plane, and then we'll add the next plane. And we'd have this. So this would be the plane x equals 1 slicing through the paraboloid. And as we look right here, so I can actually see the y-axis is moving this way. At this point, I see that the slope is significantly steeper than it was before. In fact, it kind of looks like just from here over, this would be 1 unit, and I would go up 1, 2, 3, 4 before I sort of connect to the top. And so a slope of 4 seems pretty consistent. So it is kind of cool that our differentiation technique can somehow find the slopes of these slices and dices of a surface without me, well, having to graph the slices and dices in the process. So we've seen that we're able to compute the slope of the graph of f of xy at a point x naught y naught in the x direction by the formula. We take the function, we keep x as a variable, but we replace y with a constant. Then we differentiate this function with respect to x, and we plug in the point x naught at the very, very end. Similarly, if we wanted to work out the slope of the graph of f of x at the point x naught y naught in the y direction, we take the function f of xy. We treat y as a variable, so we'll plug in x naught for the value x. Then we'll take the derivative of this in the variable y, since we got rid of the variable x, and then we'll plug in y equals y naught. Now this phrase right here, slope of the graph of the function at the point in the direction, is a mouthful. And so we're going to shorten it down a little bit. We're going to introduce, first off, a new symbol to describe this operation. And this symbol is going to look like well, it's supposed to look like df dx at the point x naught, y naught. But the problem with df dx is that that means one variable derivatives, and we're not quite doing that. So instead, we're going to use a symbol called del, which is sort of a curvy-looking d. Del f del x is a way of indicating to the reader that this was a function who was originally of two variables, but you were only using the x value as the variable. You were keeping the y value as a constant. So you can kind of make a guess as the symbol we're going to pick for this guy. We're going to use del f del y at the point x naught, y naught. Again, the dels, the curvy d's, let me know that I have more than one variable in this problem, and the y lets me know that y was the one we were treating as a variable, x we were treating as a constant. These objects right here are going to be called partial derivatives. This is the partial derivative in x, this is the partial derivative in y. Now, what the word partial means, well, we're going to have to get to that in a bit right here. But the basic idea is that a partial derivative is what you get by differentiating a function of two variables when you're treating the other variable as a constant. So as an example, if f of x, y is the function 2x squared plus 3xy squared plus y cubed, find the partial derivative of f with respect to x at the point 1, 3, and find the partial derivative of f with respect to y at the point 1, 3. So if I wanted to work out the partial derivative of f with respect to x at the point 1, 3, remember that this is just shorthand notation. It's saying we're going to treat x as the variable, so I want to think of y as a constant. So I'm going to take my function f, keep the variable x, but plug y equals 3 in. And then I'll take the derivative of it, and I'll plug in x equals 1. And that's what this symbol means right here. So that means we're going to take the derivative of, well, let's see. If I replace 3 into my formula here, I'm going to have 2 times x squared plus 3 times x times 3 squared plus 3 cubed. So that means I'm going to have to take the derivative of 2x squared plus 27x plus 27, and then I'll plug in x equals 1. So when I differentiate that, I'll get 4x plus 27 evaluated at x equals 1. That's 4 plus 27, or 31. On the other hand, if I wanted to work out del f del y at the point 1, 3, what this is telling me is it's saying that y is the variable, which means that x I'm going to treat as a constant. So I'll take the function f of xy, but I'll replace x by 1 and keep y running around as a variable. And now I can take the derivative. So essentially all that symbol is doing is it's telling me which variables I need to plug in as constants before I take a derivative. So that means I want to take the derivative. Let's see, if I plug in x equals 1, I'm going to have 2 times 1 squared plus 3 times 1 times y squared plus y cubed. So that means I'll take the derivative of the function 2 plus 3y squared plus y cubed, evaluated at y equals 1. So let's see, that's going to get me, the derivative of 2 is 0, the derivative of 3y squared is 6y, the derivative of y cubed is 3y squared, and if we plug in, oops, not y equals 1, sorry about that, it was y equals 3 the whole time. Y equals 3, we're going to get 18 plus 27, and 18 plus 27 is 45. And so those would be our two different slopes. Let's redo this problem, but let's make one slight change. Let's go and take the function, but now let's just find del f del x and del f del y. In other words, let's do this for every possible point, not just the point 1, 3. Well, how would that work? So I want to take del f del x. So what does that mean right here? Well, this means you take the function f of xy, you treat y as a constant, and then you differentiate it with respect to x. So, well, how will that work here? So I've got 2x squared plus 3xy squared plus y cubed. Except now, I want to think of this as 2x squared plus 3y squared times x plus y cubed. And I'm grouping it this way because I'm thinking of all of these terms as constant. So now when I differentiate this expression, what would I get? Well, the derivative of 2 x squared would be 4x. The derivative of 3y squared times x, well, the derivative of a constant times x is the constant. So we'd get 3y squared times, well, 1. The derivative of x is 1. And the derivative of y cubed would be 0 because y is a constant. And so that gets me 4x plus 3y squared as the derivative of f with respect to x. Notice that if we were to plug in the point 1, 3, we would have gotten 4 times 1 plus 3 times 3 squared. That would have been 4 plus 27, which would have been 31. And that agrees with what we got last time. On the other hand, if we wanted to work out the partial of f with respect to y, what that means is we're going to take the function f of xy, but now we're going to treat x as a constant. I don't have a specific value to set it to, so just keep x being constant in the back of your mind here. And then we're going to go and differentiate this with the variable y. So we want to take the derivative of 2x squared plus 3xy squared plus y cubed, where this and this are now constants. At least that's what we're thinking of. You gave me a specific point and we would plug that point in. And so let's see, when we differentiate this, we're going to get the derivative of the first term is 0 because 2x squared is a constant. The derivative of the second term, well, constants come along for the ride. The derivative of y squared is 2y. And then we'll get 3y squared on that last bit. So if I clean this up, I'm going to get 6xy plus 3y squared. And that's my derivative, my partial derivative of f with respect to y at any point you pick. Now if I were to go and plug in the point we had just done, the point 1, 3, this would come out to being 6 times 1 times 3 plus 3 times 3 squared. And that would be 18 plus 27, and that would be 45, which is what we got last time. Compute the equation of the line tangent to the graph of f of xy equals x squared plus xy plus y squared in the x direction at the point xy equals 2, 3. So let me kind of draw a cheesy picture, not a scale picture, but just something that helps me get some sense as to what's going on right here. So here's the graph, which is a surface who passes the vertical line test. I've got this input point of 2, 3. And so that hits the graph, say, right there. In fact, this would be the point 2, 3, and then the z value would be what I get when I plug 2, 3 into there. So f of 2, 3 would equal 2 squared plus 2 times 3 plus 3 squared, or 19. And so we want to go and find the equation of the line who's tangent to this graph, so who just sort of skims the surface of it, and I want it so that I get the line who is pointing in the x direction. So here's the line who just grazes the curve, and I want the line sort of moving in the x, I was going to say the x-wordly direction. I'm not sure if that's a word, but it sure sounds like it ought to be one. So how would we do that? The two things that we would need for the equation of a line is we would need a point, which we happen to have. It's the point 2, 3, 19. And we would need a tangent vector. I've almost drawn you the tangent vector. I want to go this way down right here. So without doing too much work, I already know that the y component should be 0, because it's supposed to be pointing along the x direction. It just has a vertical rise and an x run right here. But what is that rise and run? Would it not be x is equal to the run, y is equal to the rise? Those sound like slope information. So if we could go and find the slope of the graph in the x direction at the point 2, 3, we should be able to figure out what that rise and run is. But the slope of the graph in the x direction, that's just del f del x, evaluated at the point 2, 3. So let's go and work that out. Let's first figure out what del f del x is. So we'll differentiate the function x squared plus xy plus y squared in terms of x. So when we differentiate x squared, we're going to get 2x. When we differentiate xy, remember that y is treated as a constant, so we're just going to have y. Finally, when we differentiate y squared, well, since y is a constant, this is a constant, its derivative will be 0. And so now we can plug in the point in question. 2, 3, my x and y values. And so that's going to get me 2 times 2 plus 3, which is 7. So, okay, my graph is apparently not to scale because it's supposed to be rising as I move to the right. But this tells me that the slope goes up 7 units for every 1 unit to the right I go. So a vector who is parallel to the line, well, if x were to increase by 1, then the y value would increase, or the z value in this case, since z measures up, would increase by 7. And so this would be the tangent vector to this line. And now I have the 2 points, or the 2 things I need for the line. Let's go and write its equation down. We would have x, y, z equals the x naught values, 2, 3, 19, plus the vector values, 1, 0, 7, times t. And so, cleaning that up, that's x is equal to 2 plus t, y is equal to 3, and z is equal to 19 plus 7t. And so there's the equation of our tangent line. Now granted, it's a little bit hard to see that that's the tangent line. Given my cheesy picture, I didn't make any attempt to plot this surface. But let's go and just have Maple do it for us, and see whether or not the surface and the line do appear to be tangent. So here's a rendering of the surface we were just looking at, together with that line. And you can see the line just sort of seems to graze the surface right there, and if we stare at it just from the side, I'd call that pretty tangent. So it looks like we did get the equation of the tangent line after all. So let's make a couple more observations about how partial derivatives work. So suppose you happen to have a function of 2 variables. In Calc 1, there was 2 different sort of notations for functions, right? If you had a function who was f of x, you could write it as df dx. Or you could write it as f prime. And if we set it equal to its y value, as its output value, we could also write it as dy dx, or we could write it as y prime. So each one of these notations has analogs over on the 2 variable side. So since it's traditional to have the output variable for a function of 2 variables be called z, we can use the symbols del f, del x to mean the partial derivative of f with respect to x. We can also write down del z del x if we've labeled z as being the output variable. Now unfortunately, we don't have the prime notation. You know, prime is kind of unambiguous, and we don't use like prime x and f prime y. That doesn't work, although we do something pretty close to it. So the analog of the prime notation is we subscript, so we can write this as f sub x, or as z sub x. And all of these symbols denote partial derivatives of f with respect to x. And similarly, we can use del f del y, or del z del y, or we can use f sub y, or we can use z sub y, all of which to indicate the partial derivative with respect to y. So, as an example, if z is equal to the sine of x squared y plus x to the yth power, find zx and del z del y. So what do each of these things mean? Well, this is just notation for partial derivative with respect to x. So this just means del z del x. And so this means we want to take the derivative of the function sine of x squared y plus x to the y, where we're treating the variable y as a constant. So let's work our way through this thing. If we were to differentiate the first piece, sine of x squared y, well, that's the chain rule. The chain rule would say that the derivative of sine of blank is cosine of blank times the derivative of blank. And then we'll fill in the blanks. Now let's just keep going on with this part while we're still on the trail of the derivative here. To differentiate x squared y, I don't need to use the product rule because y is a constant. So y is going to come along for the ride. The derivative of x squared is 2x. And so the derivative with respect to x of sine of x squared y is cosine x squared y times 2x times y. Or 2xy times the cosine of x squared y. Now let's focus on this bit. So how would you differentiate that? Well, this is x raised to a constant power. So this is a power function. And the rule for x raised to a constant power is you drop the power down, and then you subtract 1 from the power. And so our derivative will be this expression right here. 2xy cosine x squared y plus y times x to the y minus 1. And that would be z sub x, or the partial derivative of z with respect to x. Let's now work out del z del y. So del z del y, that's just going to be the partial derivative with respect to y of the function sine of x squared y plus x to the y, where this time we're treating the x's as the constants. If we differentiate this first piece, the sine of x squared y, that's going to be a chain rule example. The derivative of sine of blank is cosine of blank times the derivative of blank. The blank is x squared y, and so the derivative of x squared y is going to be, well, do you need to use the product rule? No, because x squared is a constant, so constants come along for the ride, and the derivative of y is 1. And so this first piece will get me x squared cosine of x squared y. Just notice the comparative difference between these two terms right here. It makes a big difference who's the variable and who's the constant. That difference is going to be highlighted even more in this next example. So I want to go and differentiate this guy. But this guy is not a power function, because now the variable is in the numerator. And so this is an exponential. So if I prep it, this is e to the ln of x times y. This is actually a function of e in disguise. So when I want to differentiate this piece, well, the derivative of e to the blank is e to the blank times the derivative of the blank. Now, the derivative of ln of x times y, remember, ln of x is a constant. And so the derivative of y is just 1. And so this is going to get me ln of x times e to the ln of x times y. But of course, we can unprep this expression and rewrite this as x squared times the cosine of x squared y plus ln of x times x to the y. And that will be del z del y. If f of x, y, z is equal to the function x squared z plus x times e to the z plus y times the sine of xy, compute del fx, del f del y, and del f del z. Wait a second. F of x, y, z? Del f del z? How are we supposed to be able to do this? I can't even graph a function of 3 variables, so how am I supposed to be able to work out these slopes right here? Well, this is a common theme in our Calc 3 experience, is if we can do it for 2 variables, we can do it for 3, even if we lose the geometric meaning. Right? This symbol right here just means treat x as a variable and everybody else as a constant. Treat y as a variable and everybody else as a constant. So presumably, it makes sense to say del f del z means to treat z as a variable and everybody else as a constant. So let's see if we can work our way through this. So let's start off with del f del x. So del f del x means to take the derivative, treating x as a constant, of the expression x squared z plus x e to the z plus y times the sine of xy. So as we work our way through this particular derivative right here, well, let's notice on the first piece, z is a constant. So I don't need to use the product rule. I can just take the derivative of the first piece, 2x, and multiply by z. In the second piece, again, e to the z is a constant. So I don't need the product rule. Constants just come along for the ride, so the derivative will be 1 times e to the z. And last but not least, I've got this piece. Cool thing is, I don't need to use the product rule again. It's y is a constant. So y will come along for the ride. The derivative of sine of blank is cosine of blank times the derivative of the blank. Well, the derivative of x times y, well, again, y is a constant, comes along for the ride. The derivative of x is 1. And so when we clean this thing up, we're going to get 2xz plus e to the z plus y squared times the cosine of xy. Alright, now let's focus on the next bit, del f del y. So I want to take the partial derivative with respect to y of x squared z plus x e to the z plus y times the sine of xy. So, I need to differentiate this first piece. Do you see it? This whole piece is a constant. It has no y's in it, so its derivative is going to be 0. Same is true for the second piece. X and z are constants. Y is the only variable. This is a constant. Its derivative will be 0. So when I get to this last piece, well, now I have y times the sine of xy. That's going to involve the product rule. So we'll get the derivative of the first times the second, plus the first, which is y, times the derivative of this. The derivative of sine of blank is cosine of blank, times the derivative of the blank. The derivative of xy. X is a constant, comes along for the ride. The derivative of y is 1. And so that's just going to get me sine of xy plus xy times the cosine of xy. Finally, we can take a look at del f del z. Del f del z means we're going to take the partial derivative with respect to z of x squared z plus x e to the z plus y times the sine of xy. So we focus on this first piece. In the first piece, x squared is a constant. Constants come along for the ride. The derivative of z is 1. In the second piece, x is a constant. Constants come along for the ride. The derivative of e to the z is e to the z. The third piece, everything in it is constant, and so its derivative will vanish. So that tells me that my last term is x squared plus x e to the z. Now, what if you had a function like this one, x squared y plus y cubed plus, say, x times the sine of y? We can take its partial derivatives. We would get, in this case, 2xy plus the sine of x, or sine of y, sorry, and the partial derivative of f with respect to y would be x squared plus 3y cubed, or 3y squared, plus x times the cosine of y. Now, these are, again, functions of x and y. So we could differentiate these one more time. We could take the partial derivative of f with respect to x, and we could differentiate it with respect to x. Or we could take the partial derivative of f with respect to x and differentiate it with respect to y. We could take the derivative with respect to y of the derivative with respect to x. Well, let's do that really fast. So if we take the derivative of this expression right here with respect to x, we're going to get 2y plus the derivative of sine of y with respect to x is 0. And so that gets me 2y. On the other hand, if we take the derivative with respect to y of the derivative with respect to x, well, let's see, the derivative with respect to y, we're going to get 2x, and the derivative of sine is cosine of y. And, of course, we could do the same thing over here. We've got this partial derivative of f with respect to y. But since it's a function of two variables, we could repeat. We could take the derivative with respect to y of this, or we could take the derivative with respect to x of it, and we would get two brand new partial derivatives. So let's try this out. If we take the partial derivative with respect to y of this formula right here, well, let's see, the derivative of x squared with respect to y is 0, the derivative of 3y squared with respect to y is 6y, and the derivative of x cosine y, since I don't need to use the product rule, is negative x times the sine of y, or 6y minus x times the sine of y. And last but not least, if we take the partial derivative with respect to x of the partial derivative with respect to y, let's see. So again, I want to take the derivative of this beastie right here with respect to x. So the derivative of x squared is 2x. The derivative of 3y squared is 0 because there's no x's in it. And the derivative of x cosine of y is a constant, comes along for the ride. The derivative of x is 1, so we're going to get 1 times the cosine of y. And so if I clean that up, I get 2x plus cosine y. So every function has two partial derivatives. These two partial derivatives give rise to two more partial derivatives each, for a grand total of 4 second partial derivatives. To say this again, so we've got the function, we have the first partial derivatives, 2 of them, and then we have second partial derivatives, 4 of them. There's one other thing to note about these partial derivatives right here, is that when we took the partial derivative of f with respect to x followed by y, we got 2x plus cosine of y. And when we took the derivative of f with respect to y and then followed by x, we got 2x plus cosine y. These two things matched up. And that's not quite an accident. Let's compute del squared f del y del x and del squared f del x del y if f of xy is equal to x sine of xy squared. So how do we interpret a symbol like this? Well, how we interpret is we write the top down as del f, and we just keep the bottom the way it was before, del f del y del x, and we parse it like this. This is the derivative with respect to y of the derivative with respect to x of f. So what we're going to do is we're going to take the function x times the sine of xy squared, and then we're first going to take the derivative with respect to x of this guy, and then we're going to take the derivative with respect to y of it. So notice that even though it's written yx, the order is xy. So let's go and take these derivatives and see what we get right here. Let me focus on this part first. I'll do a little dog leg right here. If I want to take the partial derivative with respect to x of x times the sine of xy squared, I'm going to have to use the product rule on this, because I have x's in both pieces. So the product rule says it'll be the derivative of the first times the second plus the first times the derivative of the second. The derivative of sine of blank is cosine of blank times the derivative of blank. The blank is xy squared. X is the variable, y is a constant, so the derivative should just be 1 times y squared. And so if we clean this up, this is sine of xy squared plus x times y squared times the cosine of xy squared. So this is the thing I need to plug back into here. So we want to take the derivative with respect to y of sine of xy squared plus xy squared times the cosine of xy squared. Let me get myself a little bit more space here. Alright, let's do this. For this first piece, since it doesn't have any products in front of it, we'll just use the chain rule. The derivative of sine of blank is cosine of blank times the derivative of blank. The blank is xy squared. But this time we're differentiating it with respect to y, and the derivative with respect to y is going to be x times 2y. X comes along for the ride. The second portion is going to involve the product rule. So we'll differentiate the first. The derivative of xy squared we just said was x times 2y. So the derivative of the first times the second plus the first times the derivative of the second. The derivative of cosine of blank is negative sine of blank times the derivative of blank. The blank is xy squared. The derivative of that with respect to y is x times 2y again. So if we clean this up, we have 2xy times the cosine of xy squared. We have 2xy times the cosine of xy squared. And then here we're going to have negative. We have an x and an x. We have a 2. We have a y squared and a y to the first power, so y cubed, times the sine of xy squared. And noting that these two guys can be combined, that gives me a grand total of 4xy times the cosine of xy squared minus 2x squared y cubed times the sine of xy squared. And since there's a 2xy I can pull out of all these guys, I'm just going to. And so we'll have 2xy times 2 cosine of xy squared minus xy squared times the sine of xy squared. Whoo, Nelly. 1 second order partial derivative down. 1 to go. So remember, to interpret this guy, we're going to write it as del times f over del x, del y, and then we'll parse it, reading from essentially right to left. So this is going to be the partial derivative with respect to x of the partial derivative with respect to y of the function x times the sine of xy squared. Now notice that when we differentiate this expression with respect to y, I don't need to use the product rule on it, because the x just comes along for the ride. So we're going to have the cosine of blank times the derivative of blank. The blank is xy squared, and when we differentiate with respect to y, we're going to get 2xy. So that means we're going to take the partial derivative of 2x times y times the cosine of xy squared. So now let's differentiate this with respect to x. We'll have to use the product rule on it. So we're going to have, well, let's see what we get here. The derivative with respect of the first guy is going to be 4x times y is a constant, comes along for the ride, times the second piece, plus the first times the derivative of the second. The derivative of cosine of blank is negative sine of blank times the derivative of blank. The blank in this case is xy squared. The derivative of xy squared with respect to x is y squared. So if we clean this up, that's going to be 4xy times the cosine of xy squared minus 2x squared y cubed times the sine of xy squared. And just like in the last example, the derivative with respect to x followed by the derivative with respect to y, or the derivative with respect to y followed by the derivative with respect to x, matched exactly. Does that happen all of the time? No. However, we do have this almost as good result. It's called the equality of mixed partial derivatives. If either del squared f del x del y or del squared f del y del x is continuous, then both of the partial derivatives are equal to each other. So if you work out one of them and find out that he's continuous, then the other one must be the same thing. Do note that there's a proviso to this. If f happens to be discontinuous at a specific point x naught y naught, then the mixed partial derivative del squared f del x del y at the point x naught y naught, and the mixed partial derivative del squared f del y del x at the point x naught y naught, they don't have to match. So we need to keep that in mind. As one last example, let's compute f sub zxx at the point 1, 2, 3 if f of xyz is equal to x to the fourth y squared z cubed. So the first thing I got to do is decode what this is right here. I know that f sub z is supposed to be the partial derivative of f with respect to z. So what should f sub zx mean? Well, since I know what f sub z is, I should interpret it like this. This means take f sub z and differentiate it with respect to x. And so this is just another way of writing the partial derivative with respect to x with respect to z. And then if I want to figure out what f of zxx is, well, now that we've figured out what this part is, we're going to take the derivative of it with respect to x. So this will be the partial derivative with respect to x of del squared f del x del z, or del cubed f del x del z. So this guy represents a third derivative, and it represents a third derivative in the order of z first, x second, and x third. The nice part about the subscript notation is at least the derivatives appear in their correct order. In the del notation, they appear in reverse order. So let's actually compute. So to work out f sub z, we need to take the partial derivative with respect to z of x to the fourth y squared z cubed. So when we differentiate that, x to the fourth y squared is a constant, comes along for the ride. The derivative of z cubed is 3z squared. And that gets me 3x to the fourth y squared z squared. Now we're going to take that and differentiate it with respect to x. So I'll take the partial derivative with respect to x of the thing we just got, 3x to the fourth y squared z squared. So the 3y squared z squared is a constant, comes along for the ride. The derivative of x to the fourth is 4x cubed. And so that will get me 12x cubed y squared z squared. Finally, to work out f of zxx, that means we're going to take the derivative with respect to x of the thing we just found, 12x cubed y squared z squared. So the 12y squared z squared is a constant, comes along for the ride. The derivative of x cubed is 3x squared. And so that'll get us a grand total of 36x squared y squared z squared. Finally, to do f of zxx evaluated at the point 1, 2, 3, we'll take our function 36x squared y squared z squared, and we'll plug in x equals 1, y equals 2, z equals 3 to get 36 times 1 squared times 2 squared times 3 squared. 1,296. And so there's our final answer.